You ever stop and think about the hidden technologies that make our modern world, well, work? The stuff that's silently humming away in the background, doing these incredible jobs at mind-bending speeds. Well, today, we're going to pull back the curtain on one of the most important and maybe one of the most misunderstood of them all.
So just think about this for a second. What kind of chip do you think is behind all of this? I mean, something fast enough for high-frequency stock trading, where a millisecond can literally mean millions of dollars. Powerful enough to handle all the data for our cell phone networks. And, get this, reliable enough to be shot into deep space on a rocket. It's definitely not your everyday computer chip. No, the answer is something way, way more adaptable.
And that answer is the FPGA. It's the unsung hero, the secret weapon behind some of the most demanding jobs on and off the planet. So what in the world is an FPGA? To really get what an FPGA is, you have to think of it like a hardware chameleon. Seriously, it's a chip that can completely change its identity long after it's been made and shipped out of the factory. Okay, the full name is a bit of a mouthful. Field Programmable Gate Array. But the only two words you really need to remember are field programmable. See, unlike pretty much every other chip, which has its function burned in permanently, an FPGA is a blank slate. You can program its internal wiring in the field, out in the real world, to become whatever custom circuit you need it to be at that moment. That's the magic right there.
Now, the absolute best way to wrap your head around this is with an analogy I really love: Legos. So let's use Legos to see exactly where FPGAs fit into the whole universe of computer hardware.
All right, so on one end of the spectrum, you've got your CPU, or your microcontroller. That's the brain in your laptop or your smart coffee maker. It's a total jack of all trades. It can do a lot of different things, but its basic hardware structure is totally fixed. Then, on the complete opposite end, you have something called an ASIC. That stands for Application-Specific Integrated Circuit. This thing is a master of one. It is custom built from the ground up to do one thing, and one thing only, with insane speed and efficiency. Okay, let's bring the Legos back in. A CPU? That's like a pre-built Lego car. Sure, you can drive it around and do car stuff, but you can't really change it. It's a car. An ASIC? That's like a single, unique Lego piece that was custom molded for just one spot in a Lego set. It's absolutely perfect for its job, but it's permanent. It can't be anything else. So, where's the FPGA? The FPGA is the giant box of individual bricks. You have total freedom. You can build a car today, a spaceship tomorrow, take it all apart, and build a castle the next day, all from the same box of pieces.
So, if an FPGA is this big box of Lego bricks, what are those individual bricks actually made of? Right? How does this magical shape-shifting thing actually happen? So the fundamental brick, the core building block inside every single FPGA, is this little thing called a lookup table, or a LUT for short. Just think of a LUT as a tiny programmable logic machine. An engineer can tell it how to behave. And by wiring together millions of these little LUTs on a single chip, you can build up these incredibly complex and totally custom digital circuits from scratch. And the process for making this happen? It basically boils down to 3 steps. First, an engineer writes code to describe the hardware they want to build, using a special language like Verilog or VHDL. Then, a software tool takes that code and translates it into a configuration file, basically a giant instruction manual for all the LUTs. And finally, that file gets loaded onto the FPGA, which physically rewires itself on the inside to become that brand new custom circuit. It's pretty wild.
Okay, this all sounds incredibly powerful, but you can probably guess it's a bit more complicated than just using a normal chip. So why would you choose an FPGA? What are its unique superpowers that make it worth the effort? This table really shows you where the FPGA hits the sweet spot. See, compared to a cheap and simple microcontroller, it offers just massively higher performance because it can do so many things at once. But then compared to a super fast but totally rigid ASIC, it gives you complete flexibility. FPGAs live in this really interesting middle ground. They're way more powerful than a microcontroller, but way more flexible than an ASIC. The trade-off is they tend to be a little less power efficient than either of the extremes. And you know what? There is no better way to understand these trade-offs than to look at the hardware arms race that happened in the early days of Bitcoin mining. It is a perfect real-world case study. So in the beginning, people were just mining Bitcoin on their regular home computer CPUs. It worked, sure, but it was slow and burned a ton of electricity. Then, some really clever miners figured out they could program FPGAs to do the exact same math, but way faster and using less power. This made them way more profitable, and it was kind of a golden age for FPGAs in the crypto world. But eventually, once the mining math was totally locked in, companies invested millions to create ASICs, chips that did nothing but mine Bitcoin at the absolute maximum speed and efficiency possible. For that one specific stable job, the ASIC was king. This story just perfectly shows the role of each type of chip.
Okay, so if an ASIC can eventually beat an FPGA at a stable task, then why are FPGAs still so important? Well, because most of the real world isn't stable. Algorithms change, communication standards evolve, and new ideas need to be prototyped and tested fast. And that brings us to the really crucial point. FPGAs are the absolute champions in certain areas. They dominate when you need massive parallelism, doing tons of things all at the same time, like processing high-definition video. They're essential when you need that maximum flexibility, the ability to update the hardware's function after it's already sitting on top of a cell tower or orbiting the Earth in a satellite. And they're perfect for connecting to weird, custom sensors that standard chips just don't know how to talk to.
This quote from our source material really just nails it. FPGAs are not for your toaster. That's an application that is super cost-sensitive. No, they are for the high-stakes stuff, where getting that extra speed and adaptability is absolutely worth the price. And that leaves us with a really fascinating thought to end on. In a world that's just moving faster and faster, where AI models are changing by the month and communication protocols are always evolving, the whole idea of a fixed, permanent chip starts to feel, a little old-fashioned, doesn't it? The power to literally reshape hardware to meet a new challenge is just immense. So the real question isn't just about what FPGAs do today, but whether their reconfigurable nature is actually a glimpse into the future of all computing.